Okay, you want 3 classes. I was not expecting that answer. I was expecting the opposite. Chalo. Too long. Look, Vijay Shah is saying too long. Look, tomorrow class will be, let me tell you why I am saying, look, tomorrow is Saturday. Okay, so Saturday. Okay. Tomorrow class will anyway be long because yes, one external, yes, very nice. So tomorrow we are going to cover external and if and okay, so it is external heat transfer. And because so many concepts will be covered before we go to external, so it will be anyway be long class. Okay, so it will go around 2 hours 30 minutes. Let's say I'll try to finish it in 2 hours 15 minutes or something, but it will anyway be long. I cannot do anything because it is concept. Now let's talk about Sunday. So Sunday it is internal convection or heat transfer through pipes and all. Okay, and open channels, and then we have free convection, then we have boiling. So 3 concepts we need to cover. Now this concept can be covered in 2 hours, let's say. So the next day, whatever we class we have the next week, I don't know, whatever the third class, then only questions will be left. So what we can do is we can take 1 hour here and we can finish everything on convection. So HMT will be over for you. Why do you want to wait 3-4 more days just to have one extra class? I don't know. You would suggest me, I'll do as the majority will say. So I can distribute it into 2 classes or I can finish it in 3 hours. So it's up to you. Whatever you want. I mean, I will go with the majority. So whatever we are, I think 4 or 5 people in total. Okay, Sean is saying 2 long classes. Vijay is saying 2 long classes. Sahil will also come. I don't know if he has come, but he can also suggest. Shruti wants 3 classes. The Sahil has not come yet. Okay. Sunday we can start at 9. No, yaar, Sunday no, not 9. I was actually thinking of maybe we can start later sometime. Is it okay? I don't know. We will talk tomorrow. So I don't know. Like we can discuss it if you are all interested. We can start later in afternoon or later in night, evening. I don't know. Let's talk about that tomorrow. So if everyone, like the majority will say, we can do accordingly. If you say 9, then we can do at 9 as well. No problem. Okay, chalo. Let's start today's class. Chalo. Tomorrow class is at what time? What time is your tomorrow class? Yes, 5:50. Chalo, theek hai. Let's move on. So radiation is still left. We are going to cover radiation today, lecture 10. And in 12 or 13 lectures, we will close your HFT. ठीक है, चलो. So this is my introduction. You already know me, so there is no point. MTech from IIT Kharagpur, MSc from Politecnico di Milano, 5+ years of teaching experience, and this was my AIR score. ठीक है, चलो. Now, till now, I think you have all seen the lecture. If not live, then like the recorded one. So we have talked about basic introduction. We have talked about various terminology, various rules, various laws or various rules. And we have talked about the most important concept and very frequently asked concept of, what was the concept that we covered? Anyone? Quickly. View factor, yes. View factor, shape factor, configuration factor. Very important. Every year you will get, every second year, or every alternate year you can get at least one question. Sometimes even in every year, continuously 2 or 3 years, you will get a question from view factor. Now, today we are going to move on radiation electrical analogy. Like we did that analogy, resistance analogy in conduction and convection. Similar resistance analogy actually we are going to do for one paper only, sir. What do you mean? Okay, mechanical. Yes, yes, only one paper. That is actually good for you. Okay. Otherwise, sometimes some people get tougher paper. Some people get easier paper, and then normalization happens. So it's one paper is actually good. Everyone will be measured at the same scale. I am not sure. Maybe students are less. I don't know because students are less, or because it's like this time they have increased centers as well. Okay, so I think they have made enough centers this time, so they have enough capacity to hold students. So could be any reason. They have not specifically given the reason, but it is good for the aspirants. It's good because then you don't have to worry about the level of questions in other paper. You don't have to worry about normalization. So whatever you do it on your own. ठीक है ना? चलो. So today we are going to define the resistances. What resistances? Radiation resistances. Resistances in radiation heat transfer. Okay. Now, there are two terms that we need to define. First is irradiation. Irradiation, and second is radiosity. What is irradiation? So total radiant energy incident. Incident. Okay. जो पड़ रही है, whatever is incident on the surface is called as irradiation. Total radiant energy incident upon the surface per unit time, per unit area. Okay. Now some of it may be reflected to become a part of radiosity. Okay. Some portion of the incident radiation, look, it is the incident radiation. It is the falling one. Okay. Now, whatever is incident, it could be absorbed, it could be transmitted, or some portion can be reflected. Some portion can be reflected. Now, what is going out from this surface? What is going out? Look, because of the reflexivity of the surface, it is the surface property, right? Absorptivity, transmissivity, reflexivity, it is the surface properties. Now, because I'm sorry, because of the reflexivity of the surface, some portion of this G, is going out of this surface. So it is in, it is out. Okay. Now, this body is at certain temperature, right? Let's say T1. And if this T1 is greater than 0 Kelvin, then this body will be radiating heat, radiating energy, or it will have electromagnetic waves going out because of its temperature. Every body at all temperatures greater than 0 Kelvin will be radiating electromagnetic waves because of its temperature. Higher the temperature, higher the intensity of the electromagnetic waves or the radiations. But everybody at all temperatures radiate heat. Okay. So this is emitted radiations because of its what? Why these emitted radiations are coming out? It is because of its, tell me why this. Yes, because of its temperature. So this is because of its reflexivity, and this is because of its temperature. Now, how do we write this? It is E is equals to emissivity into EB. Yes, the body is at temperature greater than 0 Kelvin. Okay. And this is because of its reflexivity. Everything that is going out is called as radiosity. Everything that is going out is radiosity. Okay. Now, total radiant energy leaving a surface per unit time per unit surface area. just 1 second, sorry. Okay, total radiant energy leaving a surface. What is going out? Irradiation is basically what is incident. Radiosity, what is going out. Sum of the radiation emitted from the surface and the reflected portion of the radiation incident. Okay, chalo. So, radiation electrical analogy. This is what we are going to do. We are going to define resistances, electrical resistance. Now, this is one body. This is one body. It is a temperature T1. And here we have some surrounding. Here we have some surrounding. Even if surrounding is not there, still electromagnetic waves will go out. Okay. But of course, it's not vacuum. So there are some surroundings. Okay. Now, if I want to define radiosity, how do I do that? Radiosity will be equal to, what is radiosity? Will be equal to what? Sum of total radiations going out. Okay. So I can say radiations because of its temperature plus radiation going out because of its reflexivity. Okay. Now, how can I write this? This is emissivity of the radiation emitted if this would have been a black body. Okay. Plus rho into G. Rho into G. Now, we know we have done energy balance, right? Energy balance. And what do we have? Alpha plus rho plus transmittivity is equals to 1. Now it's a opaque body. It's a opaque body. Okay. So as transmissivity is equals to 0, so can I say alpha plus rho is equals to 1? And can I say rho is equals to 1 minus alpha? Yes, I can say that. Okay. So now of radiosity, what is radiosity here? Radiosity is equals to emissivity e to the power b plus 1 minus alpha g. Okay. Now, we also know that this is maintained at a constant temperature T1. Okay. And we all know that Kirchhoff's law. What was Kirchhoff's law? What was Kirchhoff's law? E is equals to A. Yes. If a real body is in thermal equilibrium, then its emissivity will be equals to its absorptivity. Okay. So, can I write J is equals to emissivity EB plus 1 minus emissivity G? Okay. Yes, I can write that. Now, can I write J minus emissivity EB upon 1 minus emissivity is equals to G? Can I say this? Is it clear? Everyone, is it clear? Chalo. So we have defined G. Now, net rate of radiation heat transfer from this surface 1. If this surface 1, which is at temperature T1, so what is the net rate of radiation? Net rate of radiation. So what will be the net rate of radiation? Of course, radiosity minus irradiation. Net rate of radiation heat transfer from the surface. What is the net rate of radiation heat transfer from the surface? So what is going out minus what is coming in. Okay, because we are talking about net rate of radiation heat transfer from the surface. Okay, chalo. So can I say Q dot net 1 per unit area is equals to J minus G. Can I say this? It is radiosity minus G. Okay. Now I have just defined G. I have just defined G. What is this? J minus emissivity E B 1 minus emissivity. So I can simplify it further by J minus emissivity J minus emissivity EB upon this. Now I can cancel this plus minus. Okay, 1 second. Here you will get plus because यहाँ पे minus है. So when you take it as common, it will take plus. Okay. Yeah, just 1 second. Okay. चलो ठीक है. Now how can I write this? Can I write emissivity EB minus J 1 minus emissivity. ठीक है. Now let me further simplify it in a way that we know our resistances. Okay. So Q dot net 1 per unit area is equals to EB minus J 1 minus emissivity upon emissivity. Is it clear? Have we seen this? Have we seen this form of equation? Have we seen this? So can I say it is the driving force, like the temperature we had, right? Temperature was driving the heat transfer. So this is the driving force and this is the resistance. Now what is this resistance? This is called as surface resistance because it is happening because of the surface properties, emissivity and reflexivity. Okay. So it is called as surface resistance. If you want me to show this, I can show it like this. For example, this is your 1 second. Sorry, I am feeling like I have a little cold or I'm about to get cold. Chalo. So if this is your body, okay, and if this is a black body, then its radiation will be EB. Okay. Now, if this is the black body, otherwise it will be emissivity EB. Okay. Now, when because of its resistances, because of its surface, it will offer some resistance. And this is your EB, this is your J, and this is your Q dot net per unit area, and this will be your surface resistance 1 minus emissivity upon emissivity. Okay. So can I say surface resistance? If you have a plate, then this resistance will be there. If you have a plate, I mean plate or any surface, it could be concave surface, convex surface, hemispherical surface, or any surface. Okay. So if you have a surface, you would have a surface resistance. Our surface is equals to 1 minus emissivity upon emissivity. And this is a surface property, as I said, because it depends upon the properties of the surface. Okay, is it clear? Chalo. Now, so we have defined surface resistance, which is equal to this. Okay. Now, for black body emissivity is equals to 1. So I can say Ri is equals to 1 minus 1 upon AI. Now 1 minus 1 will be 0 upon AI. So surface resistance will be 0 for black body. Okay, surface resistance will be 0 for black body. ठीक है, चलो. Now let us move on to the next. Now let us talk about, abhi to we have learned that if what is the radiation heat transfer by a single body, how much is going out. Now let us talk about radiation heat transfer between two bodies, two surfaces or two bodies. Okay, now this is one surface 1 is a temperature T1 and it is non-black body, so its emissivity is equals to T1. It is surface 2, it is a temperature T2 and its emissivity is T2. Okay, now let us say one is a higher temperature and second is lower temperature. So let us assume that T1 will be greater than T2. I am assuming. So T1 will have more radiations going out than the T2. Okay, now let's consider two non-black surfaces. Surface 1 is radiating total J1 radiation. What is going out is J1, right? The total radiation that is leaving surface 1 is J1. Now out of this J1, some will be lost and some will be captured by surface 2. Now how much is captured by surface 2 is given by J1 A1. If you multiply by the area, J1 A1 is what? J1 A1 is what is total energy that is going out. Okay. Then if you multiply it by F12, then you will get the fraction that is receiving by surface 2. Okay. Fraction that is received by surface 2. Okay. Similarly, radiation received by surface 1 from surface 2 is J2A2. This is the Q221. Okay. And then if you multiply it by F21, it is total fraction that is received by the surface 1. ठीक है? Is it clear? चलो. Now let us talk about how much heat Q1 to 2. Okay. 1 से 2 पे how much is falling? 1 से 2 पे what is the radiation heat transfer from surface 1 that is reaching surface 2. Okay. So by this is what is going out. Q out of surface 1 minus Q in by surface 2. J2A2 F21. Yes. ठीक है. This is radiation received by surface 1 from surface. Yeah, this is 1. That is coming in. Okay. Chalo. Now tell me one thing. Can I draw this circuit here? Okay, I'll draw that later. Now tell me what is reciprocity theorem? Reciprocity theorem. What is reciprocity theorem? Yes. A1 F12 is equal to A2 F21. Okay. So can I write the above equation as J1 minus J2 A1 F12? Can I further write it as J1 minus J2 1 upon A1 F12? Now this is the space resistance. Why this is the space resistance? It does not depend on the surface. It basically depends on the distance. It depends on the orientation of the body. So it does not depend on the surface. It depends on how the two bodies is separated, how the two bodies are separated. Okay, so this is called as J1 minus J2 by space resistance. Now, if you need to draw this diagram, then how can I draw this? So there is body J1, it is J1, it is J2. Okay, and some heat transfer is happening Q1 to 2, and it will be equal to, resistance will be equal to 1 upon A1 F12. ठीक है, sounds familiar or not? So it is called as space resistance. So 1 upon A1 F12 is your space resistance. It is because of upon how the two bodies are separated with respect to each other. ठीक है, चलो. Now, so this is a total thermal circuit. Okay, this is the total thermal circuit. If you have surface 1, then of course you will have a surface resistance. Now there is space also between them, so there will be a space resistance. Let's say this is R1, the R2 is space resistance, and again because of surface 2 is here, and every surface have a resistance, so this will be R3 surface resistance. Okay, so R1 is equals to 1 minus, now this is your, in fact, let me divide these resistances as, first, surface resistance. So if there is a surface, there will be a surface resistance. Okay, R surface, because of surface 1, will be equal to 1 minus emissivity 1 and A1 emissivity 1, and because of surface 2, it will be 1 minus emissivity 2 upon A2 E2. ठीक है. Then second is space resistance. So R space, okay, will be equal to 1 upon A1 F12. Sorry, 1 second. Sorry. ठीक है. So now if this body is at temperature T1, so it will be EB1, this will be EB2, and the space is separated by J1 and J2, and this resistance is because of the surface, this is because of the surface, and this is because of the space. ठीक है, is it clear? This one is clear or not? चलो. Now, so this is the resistance. Now let's calculate heat transfer, net heat exchange. Okay, so we have seen this diagram, we have understood this diagram, right? Now we know that R1 and R2 are surface resistance, and R1 and R2 and R12 is space resistance, if we are writing it this way. Now can I say Q dot 12 net is equals to EB1 minus EB2 1 minus emissivity 1 A1 emissivity 1 F12 A1 plus 1 minus emissivity 2 A2 E2. I can write this like. Chalo. Now let's do one thing. Let's take area 1 on the top. So if I take A1 here, A1. Now what is EB? Can you tell me what is EB? We have defined Stephen Boltzmann's law. Stephen Boltzmann, what did he say? Energy radiated from a black body will be equal to Stephen Boltzmann's constant T to the power 4. Very nice, Sean. Okay. So it will be equal to sigma T1 to the power 4 minus T to the power 4, right? Divided by 1 upon emissivity 1 plus 1 upon F12 plus 1 minus emissivity 2 A1 by A2, right? Chalo. Now this is something, the denominator, it is called as gray body factor. So I can write it like this. I can write it like F A1 sigma T1 to the power 4 minus T to the power 4 1 upon Fg one to 2. This is called as gray body factor. So I can also write it Fg 1 to A1 sigma T1 to the power 4 minus T to the power 4. Okay. So what is Fg12? What is Fg12? Gray. In fact, I have written it here. It is called as gray body factor. Okay. So Fg12 is gray body factor. Gray body factor. And it is 1 upon this total resistances. Okay. This is your gray body factor. Okay. Now, can you tell me how it is, like if we want to compare it from conduction and convection, then what is a relative term? What is a relevant term that relates to this? Do you remember that term? Yes, overall heat transfer coefficient. Okay, overall heat transfer coefficient. So it is equivalent to that, right? It is a combination of surface. There, U was the combination of conduction and convection resistances. Here, gray body factor is a combination of surface and space resistance. Surface and space resistance. Now we need to apply this. For example, we have this type of body. What is this body? We have a small, very small object in a very large space. Small object in large cavity. For example, a small plate is there in a very big hall, very big room. Okay. If they have given the dimension of room, that means it is not a big room. Okay, it is a finite room. If they have not given dimension, it means it is a infinitely large room and a very small body is inside that room. Okay, chalo. So in this case, this will only happen when area of one is very, very, very less than area of body 2. So can I say A1 by A2, it tends to 0? I can say this, right? Okay, yes, it tends to 0. Okay. Now, by whatever is radiated from body 1 will be absorbed by body 2, isn't it? So, this is one condition, and I can say F1 will be equal to 0 and F12 will be equal to 1. Chalo. Now let's talk about gray. One second. Okay, let's talk about gray body factor. So how did we define Fg? How did we define Fg 1 to 2 is equals to 1 upon 1 minus emissivity 1 emissivity 1 plus 1 upon f 1 to 2 plus 1 minus emissivity 2 upon emissivity 2 a1 by a2, right? Now, because of a condition, because a1 by a2 tends to 0, that means this whole thing will go to 0. And f12 is equals to 1. That means I can simplify this as 1 upon 1 minus emissivity 1 minus 1 plus 1. Can I write it like this? Yes. Now this will get cancelled and fg12 is equals to emissivity 1. So now next is how do you calculate heat transfer? Heat transfer. So Q dot net 1 to 2. How was it? Fg 1 to 2 sigma A T1 to the power 4 minus to the T2 to the power 4, right? A1. Now, Fg12 is equals to emissivity 1 A1 sigma T1 to the power 4 minus T to the power 4 watts. ठीक है? Is it clear? Everyone, Shruti, is it clear? Are you there? I have to check again. Who else is there? Sai, is it clear? Amit. Chalo. Next example is infinitely large parallel plate. There are two plates that are infinitely large. Their area is infinitely large. Okay. So first condition, that radiation from one is absorbed by two and vice versa. So whatever is radiating from two is absorbed by one. Okay. And area of both the plates is infinite. So can I say A1 is equals to A2 is equals to area, and they are all equal to infinite. They are all equal to infinite. 1 second. Chalo. Okay, they are all infinite. Now, also tell me one thing. Why it is a plane surface? So how much will be F11? How much will be F11? Yes, F11 is equals to 0. And Sean has told me that F22 will also be equal to 0. Now from here, if I apply summation rule, F11 plus F12 is equals to 1, that means F12 is equals to 1. And from here, if I apply summation rule, I can say F21 plus F22 is equals to 1. That means F21 is equals to 1. Okay. So from here, I have also gotten F12 is equals to F21. Also, you can also find out by applying reciprocity. The same thing you can find out. How? By A1 F12 is equals to A2 F21. Now area is same. So area will cut down and F12 is equals to F21. But by applying summation rule, we have got that they both are equal to 1. They both are equal to 1. Okay? Chalo. Now we have got all this. Now let us calculate gray body factor. Gray body factor in this case. Gray body factor. Okay. Fg 1 to 2 1 by 1 minus emissivity 1 upon emissivity 1 plus 1 upon F1 to 2 plus 1 minus emissivity 2 upon emissivity 2, A1 by A2. You can also calculate FG 2 1, but then you have to modify the equation similarly. Okay, so this is the gray body factor when you have to calculate the radiation heat transfer from 2 to 1, Okay, chalo. Now what can I do? F12 is equals to 1. F12 is equals to 1, and A1, A2 is same. A1, A2 is same. Okay. So can I write 1 upon emissivity 1 minus 1? Okay. By simplifying this, then F12 is equals to 1. So this is plus 1. Now plus 1 minus emissivity 2 minus 1, right? By simplifying this, and into 1, because A1 is equals to A2. A1 is equals to A2. Okay, ठीक है. Now minus 1 and 1 second. Minus 1 and plus 1 will be cancelled. Minus 1 plus 1 will be cancelled. So what I got here? What do I got here? 1 upon 1 minus emissivity 1 plus 1 minus emissivity 2 minus 1. Minus 1. Okay. So in this, I have, look, there they can ask anything in question, but these are very frequently asked cases. So you don't have to drive it every time. You know all these conditions. It will always be valid. It will always be valid. It will always be valid. Okay. So when it is always valid, then you can directly use this. Okay. Chalo. Now Q12 heat transfer, QG12 net. Just 1 second. Chalo. Q122 net. So how have we defined this? FG122 area 1 sigma T1 to the power 4 minus T2 to the power 4. Okay, now we can also write this A1 sigma T1 to the power 4 minus T to the power 4 upon 1 minus emissivity 1 plus 1 minus emissivity 2 minus 1. And A1 is equals to A2 is equals to area. Okay, this is how you can calculate, and this is in watts. Clear? Chalo. Now we have a finite value of E1 and E2. I mean, it is non-black bodies. These are non-black bodies. What if these are black bodies? If these are black bodies, so we know emissivity 1. I'm saying both are black bodies. So is equals to emissivity is equals to 1. Okay. Case will remain same. It is 1 upon 1 minus emissivity 1 plus 1 minus emissivity 2 minus 1. Now emissivity is equals to 1, right? So I can say 1 plus 1 minus 1. So FG12 will remain as 1. Okay. So Q122 net, which is equals to FG122 sigma A T1 to the power 4 minus T to the power 4 watts. It will simply be equal to sigma A T1 to the power 4 minus T to the power 4 watts. Only in the case of black bodies, only in the case of 12 bodies. Yes, you will see that. You will see that, don't worry. I have seen that question. I have not read it. I don't know. Okay, we'll see that. Okay, chalo. So this is clear. Is this clear? Yes or no? Okay, chalo. Let's move on. Now the last concept is radiation shield. Okay, why do you use radiation shield? To reduce heat transfer, of course. Shield is always there to reduce heat transfer. Okay, it is a thin, highly reflective, it is a body of very high reflexivity and low emissivity sheet of material which reduces radiation heat transfer between two surfaces. Okay, so if there is two surface, you put a very shiny body here to reduce the heat transfer. It will have very high reflexivity and low emissivity. So what will it do? It will reduce the overall heat transfer between two radiating surfaces. Okay. It reduces heat transfer by increasing surface resistance. By adding this, what we have done? We have increased the surface resistance. How much we have increased, we are going to see later. How much we have increased, we are going to see. But because every surface has a surface resistance, so of course surface resistance is added. Okay, and space is also distributed, so space resistance will also be there. We will see how many. Now it reduces heat transfer without actually removing heat. You are not reducing heat or removing heat from the system, but you have still reduced the heat transfer. For example, pressure vessels, coolant loop, inner shield from the intense heat generated by the absorption of nuclear radiation, and measuring thermal fluid temperature by thermocouple or thermometer. Okay, these are my examples. Now, you see, when we have this is case one. Case one, when no shield is there. Okay, so this is the case that we are already aware of, isn't it? This is the case that we are already aware of. Now, and this is the heat transfer. Okay, so EB1 minus EB2, surface resistance R1, surface resistance R2, and space resistance R12. Okay, so if there is no shield, then we have for two surfaces, we have two surface resistance and one space resistance. Okay, now what we have done, we have introduced a shield, only one shield. Case, we can use more than one shield, but we have introduced only one shield. Okay, case 2 is we have introduced one shield we have introduced. Okay, now you see, first of all, there will be a surface resistance because of surface 1 is at higher temperature, right? Then there is a space resistance here in between, space resistance between the surface 1 and the radiation shield. So this is space resistance, and then this resistance 3, so this is R1, this is R13, and this R3 is because of radiation shield surface. Okay, now next is, by this is a surface, right? This is one surface 1, and this is also another surface 2. So this shield has two surfaces that is taking part in the heat transfer. But if we talk about this surface, only the other side is taking part in the heat transfer. That's why we have only one resistance. And similarly for surface 2, we only this part is taking part in the heat transfer. So only one surface resistance. ठीक है, चलो. Now this surface resistance is because the shield is radiating or absorbing radiations from the other side. Okay. Now this is the space resistance. Now this is R3 and this is also R3. Okay. Now this is R31, R32, and this is R2. Is this diagram clear or is there any doubt? By each surface will have surface resistance, and if two surfaces are separated by a space, then you will have one space resistance as well. Okay. Now tell me, if I have introduced one shield, how many surface resistances I have? How many surface resistances I have? Can you tell me? I have total 4 surface resistances. Yes. Why 2? By adding one shield, now total surface resistances are 4. I did not ask additional. I said total. 4 surface resistance. And how many space resistances? Total space resistances? 2. Space resistance. Okay. So can I conclude here? By comparing these two and these two, that by adding one shield, I am adding 2 surface resistances. That means for every shield that you are adding, you will have additional 2 surface resistances, and 1 space resistance. For every shield that you are introducing, you will have additionally 2 surface resistances and 1 space resistances. Can we conclude this? Okay. Again, for each shield that you are introducing, you are adding 2 surface resistances and 1 space resistances additionally to what were already there. What were already there. So this is something that we know. Okay. So this is your R1. This is your R13. This is your R3. This is also same R3. This is your R32, and this is your R2. Okay, chalo. Now, so now this is case 1, no shield. This is case 2, one shield. Okay, and let us take parallel plate configuration. So I am saying F12 is equals to F21 is equals to 1. Okay, and A1 is equals to A2 is equals to area. Okay. Also, I am assuming that for both the plates, I am assuming this. If this is not the case, then I have to use the simple equation, generalized equation. If this is the case, then I can use a simplified equation. Okay. And I am also assuming that both plates have equal emissivity. Both plates have equal emissivity. So if I put this here, I will have this simplification. You can do this. There is not much to do it here. Okay, so it will be equal to, so this is the important point that you need to note. Now your gray body factor is 2 upon emissivity minus 1. 2 upon emissivity minus 1. But if you want, you can do it as well. Fg122 is equals to 1 upon 1 minus emissivity 1, and because it is equals to emissivity 2 as well, so let me write just this. Okay, minus 1 plus 1 upon, now this is also 1, shape factor is 1, plus 1 upon emissivity 2 minus 1, right? Now minus 1 plus 1 will be cancelled, and this can be added 1 upon 2 upon emissivity minus 1. Simple only, right? There is nothing much to do here. Only simple calculation. Chalo. What will happen for one shield case? Now here also we are assuming that shape factor is by, because f11 will be equal to 0, f33 will be equal to 0, f22 is equals to 0. So from here f12 is equals to 1, f32 and 31 will be equal to 1, and आई एम सॉरी f13 होगा यहाँ पे, ठीक है, and 31 and f23 will also be equal to 1. ठीक है, 2 से 3 पे कितना पड़ रहा है, ठीक है, चलो. So this is my equation. Now 1 second. Sorry. I'm gonna get cold for sure. चलो, ठीक है. So this is my earlier equation that we have learned. Now, if I apply all the assumptions here, all the assumptions that by f33 is equals to 1, f13 is equals to 1, okay, and all the emissivities are same, then I can conclude this. You can just put the values and do simple calculation, simple simplification you need to do, and you will find this. Okay. Now, if I compare these two, A and B, if I compare these two, A and B, what I can conclude? You see, what is this? What is this? This is radiation heat transfer without shield. No shield. So with introducing one shield, by introducing one shield, you have reduced the heat transfer by half of the total heat transfer, without any shield, half of the total heat transfer without any shield. ठीक है? Is it clear? So this is my conclusion. Okay. Is it clear to everyone? Shruti, Sai, and who else is there? Let me check one more time. Okay, Sai is there, Shruti is there. Is it clear? Chalo. Let us move on. Now, if I have talked about one radiation shield, what if I talk about n radiation shield? Now, what do I know? Look, adding one shield, then we have +2 additional 2 surface resistance and +1 space resistance. Okay. Now, if n radiation shields are inserted between two planes, then there will be 2 surface resistance. Additionally, 2 surface resistance for each radiation shield. Okay. And 1 for the radiating surface. For example, we had surface 1 and surface 2. So for each surface, there will be 1 surface resistance, and for each shield, there will be 2 surface resistances. Okay. So we have surface 1. Surface 1 is there. It will give you 1 surface resistance. Surface 2 is there. Again, 1 surface resistance. And one shield will give you 2 resistances. One shield will give you 2 surface resistances. Okay. Now, I can also tell you that if there are total, for example, one shield is there, then 4 resistances will be there, right? One shield is there. So 4 resistances by 2 because of surface and 2 because of shield. if one shield is there, if one shield is there, similarly you can do if there are two shields. If there are two shields, then what will happen, tell me? By two, there are two radiating surface, so there will be two resistances because of surface. And now two shields are there, total four shield resistances will be there. So total six resistances. So if I generalize this, I can generalize this and I can say that for n number of shields, the total surface resistances will be 2n plus 2. For example, let's say one shield. So I can put this 2 into 1 plus 2 is equals to 4. Now 2 shield, 2 into 2 plus 2 is equals to 6 surface resistance. So if there are n number of shields, then total, I am not saying additional, total surface resistances will be 2n plus 2. Okay, 2n plus 2. Is it clear? Total surface resistances will be 2n plus 2. And let's say everyone will have the same value, 1 minus emissivity by emissivity. Okay, if they have all, if they all have same emissivity. Now what about space resistances? By for n number of shields, the total space resistance will be n plus 2. For example, one shield, so total two space resistance. If there are two shields, so three space resistances. Okay, three space resistances, total three. Now the total resistances, so because of n number of shields, is given by surface resistance plus space resistance. Yes. What? One shield will have one additional resistance. No, look, if you see this one, you already had one space resistances here, so one was already there, but you have added one more space resistance. So by adding one shield, you have additionally one space resistance, additionally one. Okay, total two, additionally one. Okay, so this is giving me total, n plus 1 is total. Okay, so if I am introducing n shields, the total resistance will be what? Total surface resistance plus total space resistance. So this is your surface resistance, total surface resistance plus total space resistance. Okay, now n plus 1 I can take common and I can simplify it like this. Okay, but I can take 2 common, 2n plus 1, 1 minus emissivity minus 1 plus n plus 1. So I can take this common and I can get this. Okay, sure. Now it's time to summarize this. With n shields, I am getting this is total resistances. This is your total resistance with n shield. So heat transfer will be by driving force by resistance. So this will come down, resistance. Okay. Now without shield, I had this total resistance. We already know this. We already defined this, right? Here. This one. by simplifying it. So, and this is your heat transfer by driving force by resistance. So if I divide these two equations, these two equations, then this term, if I divide these two equations with N shield will be QA. I don't think I need to do this. It's very simple. Upon 2 by emissivity minus 1 N plus 1. This is with shield. And without shield is T1 to the power 4 minus T to the power 4 P upon emissivity minus 1. So this and this will get cancelled. This and this will get cancelled. And finally, you can conclude this. Okay. With N shield, this is how your heat transfer is going to reduce. Without shield, it is because you are dividing it by something. This value will be it will be less than 0, right? Yeah, less than 1, right? Because N plus 1 denominator is greater than 1 than the numerator. So it will be less than 1. That means the heat transfer is reduced with what amount that we can calculate by this formula as well. Okay, clear? Everyone? Okay, chalo. Sign is here or not? Yes. Is it clear? Chalo. Let us move on. Now let us come to the last portion, which is our numericals. We had done so many numericals that day as well, but they were focused on view factor. Now this is radiative heat transfer between bodies, between two bodies. Okay, chalo. Now, day 2003 1 mark question. It is not supposed to be 1 mark question. I think I made a mistake. It is supposed to be 2 mark question at least. But anyway, it is a question that is more than enough for us. Chalo. A plate having 10 centimeter square area each side is hanging in the middle of a room of, so let's say you have a room and a plate is hanging here. Let's say this is your 1 and this is your 2. Inside of this room is 2. Okay. Now what can I say? I can say A1 is equals to 10 into 10 to the minus 4 meter square area of plate, and room is 100 meter square. Now the plate temperature T1 is equals to 800 Kelvin and emissivity E1 is 0.6. Plate temperature is given. Temperature and emissivity of room is also given. By T2 is 300 Kelvin and emissivity is 0.3 Kelvin. 0.3 emissivity. Okay, okay. Chalo. Now Boltzmann constant is given. Total heat loss from the two surfaces of the plate I need to find out. Can you do that? Okay, let me tell you. Then from next you have to do. Okay? Chalo. Total heat loss from two surfaces of the plate is plate से कितना heat loss हो रहा है? What is the heat loss from the plate? Okay, so that is plate is our 1. Okay, so Q dot 1 से कहाँ जाएगा? 2 पे. Net will be equal to, by I know I have defined it already, A1 sigma T1 to the power 4 minus T2 to the power 4 upon 1 minus emissivity 1 upon emissivity 1 plus 1 upon F1 to 2 plus 1 minus emissivity 2 upon emissivity 2 A1 by A2. Okay. Now this will be the heat transfer. This will be the heat transfer from one side of the surface. From one side of the surface. In order to get the total heat transfer, I need to multiply it by 2. I need to multiply it by 2. So I think we know everything, right? We know everything. We know A1, we know A2, we know emissivity 1, emissivity 2. T1, T2 also. We know sigma also is given in question. The only point is F122, F122. Can anyone tell me what is F122? F122, yes, it will be 1, of course. By it is a plane surface, so F11 will be equal to 0. And then I can apply summation rule. F11 plus F12 is equals to 1. And F12 is equals to 1 because this is 0. So can you calculate this? Can you calculate this for me and tell me what is the answer? You just have to put the values. Just have to put the values. Solve it quickly. Solve it quickly and tell me the answer. Or do I need to solve it for you? Are you solving it? Tell me yes or no first. Okay, ठीक है. Solve it and let me know the answer. So, Are A, B. What is the right answer? Yes, that is correct. 27.32. Early, you did not multiply it by 2, है 27.32 or 42, whatever you are getting, is the right answer. Shruti, are you getting this? Okay. ठीक है. Let's take your time. This will come out to be 13.71. And you multiply it by 2. I don't know. I think 13.66 or something you will get. I mean, I am not very sure. And when you, let's say 13.66. Okay, 13.65. ठीक है. 6588. And then you multiply it by 2, 27.32 watts. Everything is in watts, right? So B is the right answer. Yes, Shruti has gotten the answer. Chalo. 1 second. So let us move on to the next question. A 100-watt electric bulb was switched off in a room. Okay, we have a room again. I think it is an insulated room. So nothing is going out. It is an insulated room. The heat that is generated by bulb is an electrical resistor, right? Bulb is an electrical resistor. It is the bulb. So it is electrical resistor. And in this resistor, you are giving how much? 100 watts power, electrical work that we are giving is 100 watts, and everything will be converted into heat. Okay, it was switched on in a room of this size, and it is thermally insulated, means no heat is going out. Having a temperature, inside temperature is 220 degrees Celsius. The room temperature at the end of 24 hours will be, take density of air this, and CV is equals to this. Okay. So what we are doing here, we are giving 100 watts for 24 hours. We are giving 100 watts for 24 hours. So what is the heat added into the room? Heat in, or heat not in actually, but heat added, let's say. Heat generated, let's say. Heat added into the room, because in, it is not going, it is not coming from outside, so it is not in actually, but it is heat added into the room. So 100 watts, 100 watts. So this is joule per second. And how many seconds? How many seconds? 24 into 3600 seconds. Yes. Okay. So this is how much? 24. It is, yeah, 8.64 megajoule, let's say. Megajoule. Okay. Chalo. Now, whatever heat is added, it is going to change what? It is going to change the internal energy of the room. It is going to change the internal energy of the room. Okay. So it is going to change the internal energy of the room. So it is 8.64 into 10 to the power 6 is equals to mCV delta T. Delta T. Okay, so it will be T minus 20. Now 8.64 into 10 to the power 6 is equals to mass flow rate is what? Density into volume. Density into, it is megajoule only, so I don't need dot. It is megajoule, so I don't need dot. It is density into volume. Okay. Into CV T minus 20. Now you know everything. Now you know everything. So calculate the, yes, Vijay Sai has calculated temperature. Density look is given in question and CV is given in question. Okay. So, and volume is also given in meters. So you can calculate temperature, which 467 you have calculated, and the nearest answer is D. Is it clear? Shruti and Sean, is it clear? Just give me 1 second, and I just need to do something. Just wait 1 second. चलो चलो 467.3 डिग्री सेल्सियस ठीक है चलो लेट्स मूव ऑन कॉमन डेटा क्वेश्चन ये 2009 2 मार्क क्वेश्चन ओके radiative heat transfer is intercepted between the inner surface of two very large, so it is the case of infinitely large isothermal plates. So bhaiya, when it says very large means A1 is equals to A2 is equals to area is equals to infinite. Okay. Isothermal means temperature will remain same. Temperature is not changing of the body. When the upper, so there is a upper plate and there is a lower plate. Let's say this is the upper plate. And we have a lower plate, of course, if we have a upper plate then. Okay. So upper plate, they are saying it is 1, designated as 1. So of course this will be 2. Now they are saying it is a black surface. It is a black surface means emissivity is equals to 1. And it is the warmer one being maintained at temperature. So it is maintained at temperature T1, 727 degrees Celsius. Now the lower plate is a diffuse and gray surface. It is a diffuse or a gray surface. Just one second. 727. Okay. So it is diffuse and gray. That means it will have some emissivity value. What is the emissivity? Emissivity is equals to 0.7. And it is kept at 227 degrees Celsius. Assume the surface are sufficiently large to form a two surface enclosure. What does this mean? Look, it is they are infinitely large. That means everything that is coming from one will be absorbed by two, and what is going out from two will be absorbed by one. Because let's say the end, they are infinitely large. So for example, at the end, even even if there are some radiations that are going out here, but they are significantly negligible compared to the amount that is absorbed by body 2 from body 1. Okay, because these are very large bodies, so what is lost is very, 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 very small compared to what is, yes, like long cylinder case. Yes, the same case. Okay. So that's what they are saying, that they are significantly large to form two surface enclosure. What do you mean enclosure? Means is like this. So whatever is coming from going from one will be absorbed by two. Okay. Will be absorbed by two. Okay, chalo. Now this is a black body. This is a black body. So it is going to radiate EB1. EB1, right? Now, out of this EB1, because of its reflexivity, it is going to reflect some. So, reflexivity, I can also write 1 minus absorptivity EB1, right? I can write this or not? We have proved this in the beginning. Okay. Now, this is a temperature at 227 Kelvin, 227 degrees Celsius, sorry, degrees Celsius, right? Yeah, degrees Celsius. Now, because of its temperature, it will also be emitting something. It will also be emitting something. How much it will be? It will be its emissivity and EB2. Emissivity of EB2. Okay. If this would have been a black body, then EB2 will be going out. But because it is a gray body, so what is going out? Emissivity into EB2. Just one second. Chalo. Sorry, just I'm like there's something that I'm waiting for. Chalo, ठीक है. Now it is saying assume that the surfaces what we need to calculate. Acha, now it will tell us. So it is a common data question. Let's go to the question. This is what they have given me in the question. Okay. Now the irradiation from the plate is irradiation from the plate 1. What do you mean irradiation? Can you tell me what is irradiation? Irradiation is G. Yes. Shruti is right. J is radiosity. No. Irradiation, they are asking irradiation, not radiosity. Irradiation is what is irradiation? Read this. Irradiation is G. What is incident on the surface? Incident on the surface. Radiosity is what is going out. What is going out? Okay, yes. G is irradiation. So I need to find out G. Now what will be G? By G will be whatever is going out of surface 2 will be absorbed by surface 1, isn't it? ठीक है. तो G for body 1 will be equal to what? What is going out from body 2? By emissivity EB2 plus 1 minus alpha. 1 second. Sorry. Okay. It is first of all emissivity 2. I just hope that I would not be getting cold tonight. Otherwise, I would have to postpone your class. Chalo. 1 minus absorptivity 2 and what else? EB1. EB1. It is the portion of EB1. Okay. So now, will you be able to calculate this? Will you be able to calculate this? You know everything. And you also know that emissivity equals to absorptivity also. For a real body that is in thermal equilibrium, all the conditions are satisfied. All the conditions are satisfied. Okay. So this is also you can solve. This is also you can solve. Solve it very quickly and tell me the answer. Acha, sorry. Yes. Let us see. So it is 19.5. Is everyone getting the same answer? Or Sean has done something wrong? Don't worry, Sean, you have not done anything wrong. I'm just kidding. Just give me 1 minute and I am just everyone solve and give me the answer. Tell me. So, Shruti, Vijaya, have you not solved it or what? Okay, Vijay is not here. We have to solve his question as well. I don't know where he went. Shruti, are you able to solve this? There is nothing in this, no? Tell me the answer, what you have calculated. Getting 17.6. No, why? G1 is equals to 0.7. 0.7 है ना? कितना है? Yes, it is 0.7. Okay. And then maybe you put the temperatures as different. Into sigma, it will be T to the power 4 plus 1 minus 0.7 sigma, it will be T1 to the power 4. Have you done the same thing? Have you done the same thing? Now it will be 0.7 T2. Yes, T2 is how much? 500 to the power 4 plus 0.3. This is 1000 to the power 4. And you multiply this by sigma. Multiply this by sigma. Very nice. You temperature you took reverse. Chalo, koi nahi, solve it very quickly and see if you are getting the right answer. Chalo, 19.5 you are getting, so it's time to move on. Very nice. G1 is equals to 19.5 kilowatt per meter square. ठीक है. Let's move on to the next part of this question. Two questions. If plate 1 is also diffuse, अब पहले तो earlier the plate 1 was a black body, so its emissivity was 1. Now it is also not black, it is simple gray body with an emissivity value of 0.8. So now emissivity of 1 is 0.8. The net radiation heat transfer between 1 and 2. What is the net radiation heat transfer from 1 and 2? By it will be Fg 1 to 2 sigma T1 to the power 4 minus T2 to the power 4 into per unit area. Okay, A1 is equals to A2 is equals to area is equals to infinite. Okay, is it clear? And what we have done, do you remember we have defined Fg12 for this particular case? What was it? Do you remember or not? In the same case we have defined when it is for black bodies, but when it is not black bodies, what is this? It is this. Same case we have defined. Okay, so we can directly calculate. We don't have to write everything. We can directly calculate. Chalo, calculate this. 1 upon 1 minus emissivity 1 plus 1 minus emissivity 2 minus 1. Now you know everything. Emissivity 1 is this. Emissivity 2 is 0.7. Right? Sigma also 5.67 into 10 to the power 8 minus 8. Okay. And what else do you need? T1 1000 Kelvin, T2 500 Kelvin. Can you calculate this? Fg221. What do you mean? How to write? I do not understand. Do you want to calculate Fg21? Okay. So you can do the same thing, no? Like this, what we did here is, for this body, you can talk about how is it going from 2 to 1. So instead, look, it's simple only, right? Fg 2 to 1 will be equal to, now you will take body 2 first. Okay, so 1 minus emissivity 2 upon emissivity 2 plus 1 upon F21. Okay, plus 1 minus emissivity 1 upon emissivity 1, A2 by A1. Now F21 is also 1. F21 is also 1. Right? So you can put the values. A2 by A1. A2 by A1. It's same only. A2 by A1. It is infinity. You will get as 1. Okay. So only simple thing you will get here is 1 upon 1 minus emissivity 2 plus 1 minus emissivity 1 minus 1. Simple only. Same ही रहेगा. ठीक है. चलो. So Sean and Shruti have calculated. Let me check. The question is this one, right? And the answer that you are getting is, just one second. answer that you are getting is 31. Yes, 31.7 is the right answer. Very nice. Okay. So F, what is the value of this? What is the value of FG12? Yes, 0.5957. So let's say 6. Okay. And then you put it here. Sigma, you know, T1, T2, simple only. What is there? ठीक है चलो kilowatt Q122 per unit area is equals to 31.7 kilowatt per meter square. This is my answer. Chalo, let's move on. Two large diffuse gray plates separated by a small distance. Again, the same case, GATE 2013 2-mark question. Very large, diffuse. This time, both the bodies are diffuse, like the same thing we did earlier. Same thing is going to be applied. Okay. Now, one is at 400 Kelvin. Body one, let's say. Body two is at 300 Kelvin. Okay. Emissivity, if the emissivity of both the surfaces, emissivity of the surfaces are 0.8. So now this is also 0.8. This is also 0.8. So it's more, it's easier only. It's easier only. Why? By Q12 is FG122 sigma per unit area I'm calculating. Okay. T1 to the power 4 minus T to the power 4. Now what is Fg in this case? What is Fg in this case? By same case 1 upon 2 upon E minus 1. Isn't it? We have seen this as well. Both, if both are same, so it will be 2 upon emissivity. So you can calculate this very quickly. Tell me what is the answer. So Vijay is saying A. Does anyone want to contradict this? Okay, A. Everyone is saying A. Very nice. Very nice. Very nice. ठीक है, A is the answer. ठीक है? A is the answer. Q122 per unit area is equals to 0.661 kilowatt per meter square. Very nice. Chalo, let's move on. Next question. A hemispherical surface of 1 meter radius. We have a hemispherical surface and its radius is 1 meter. Has inner emissivity. Hemispherical की बात कर रहा है तो its emissivity is equals to 1 of its roof maintained at 800 Kelvin. Now this is maintained, roof is maintained. Let's say this is R1. Okay. We can take it as 1 or we can take it as 2. Okay. So let's say this is as 2, this is as 1. Okay. So emissivity 1 is equals to 1, emissivity 2 is equals to 1 and T2 is equals to 800 Kelvin. While its floor is 1. Okay. So emissivity of 1, inner portion, this portion. Okay. Emissivity 1 is equals to 0.5 and temperature of this surface is equals to 600 Kelvin. Stephen Boltzmann's constant भी दिया हुआ है, net radiative heat transfer from the roof to the floor. So what I need to calculate here? Can you tell me? Q dot, what I need to calculate here? Q dot what? 2 to 1. Yes, because I have assumed it at 2. If I assume it at 1, then I will calculate 1 to 2. Okay, chalo. 2 to 1 I need to calculate. So very simple. What? By emissivity. 1 second. Not emissivity. Sigma. Sigma A2, because it is asking in kilowatt, not per meter square. So I need to take at least one temperature. Okay, one area. And then T2 to the power 4 minus T1 to the power 4 upon 1 minus emissivity 2 upon emissivity 2 plus 1 upon F21 plus 1 minus emissivity 1 upon emissivity 1 A2 by A1. A2 by A1. Okay. So what is not known to me? What is not known to me? F21. F21 I need to calculate. Can anyone tell me how much is F21? F21. I know one thing. What do I know from seeing this figure? I know that F11, how much is F11? 0. So F122 will be equal to 1, right? Now this is from summation rule. Now I can apply reciprocity, which is A1 F12 is equals to A2 F21. So F21 I can calculate from here. F12, which is 1, A1 by A2. Now I need to calculate A1 by A2. Okay. So A1 by A2. What is A1? Area 1. It's a plane. It's a plane. Circle. It's a circle, right? So what is the area? Can you tell me what is the area? Yes, pi r square. Very nice. It is pi r square. Now, what is area 2? A2? Hemisphere. So area of sphere by 2 तो कितना हो जाएगा? 2 pi r square. Very nice. 2 pi r square. Now pi will get cancelled. R square will get cancelled. It will be 1 by 2 or 0.5. Okay. But I need A2 as well separately. So let me calculate A2, which is 2 pi r square is equals to 2 pi 1 ka square. And I don't know, just calculate how much is it. Okay. Now F12 आ गया, F21 आ गया 0.5. It is 0.5. ठीक है. Now let me put the values. What is A2? What is A2? Can you tell me what is A2? A2 is 6.283 meter square. ठीक है. Now everything I know. I know sigma. I know A2. T2 I know at 800. T1 I know 600. Emissivity 2. Emissivity 2 is how much? 1. Emissivity 2 is 1. Okay. So this will absolutely go out because 1 minus 1 will be 0. 1 minus 1 will be 0. Now 1 upon F21. 1 minus emissivity 1, emissivity 1 into A2 by A1. And Vijaya has solved it, but he has not solved it correctly. Something is wrong. Check it again one more time. Check it again. I don't know if this area is correct. I am hoping it is correct. Anyway, yeah, it seems to be a realistic value 2 pi. Yeah. Are you calculating it? Yes or no? SF wrong. I did. What is SF? No, Shruti. Vijay has already given that answer. I have said it is wrong. Okay, shape factor. F21 you have calculated wrong, huh? Calculate it again. Now I have put all the values here. Now so you can calculate, I guess. and it's still not correct. Why this is like this? 5.67 into 10 to the power minus 8 into 6.283 into 800 to the power 4 minus 600 to the power 4. Yes, 24.93 is the correct answer. So if Sean is getting it, that means my answer is correct. Sometimes I am not very sure my answer is correct because I just do a lot of shortcuts. Chalo. 24.93 is correct. Why? What is the problem, Shruti? Vijaya? Vijaya told me shape factor he took wrong. Yes, that is correct. What was the mistake earlier? Chalo. Let's move on. This question. Year 2015 2 marks question. The total emissive power of a surface is 500 watt per meter square. Okay. Emissive power means E. Okay. At a temperature T1. अच्छा ठीक है. So it is, let's say, E1 at T1 and 1200 watt per meter square, that is E2 at temperature T2, where the temperatures are in Kelvin. Assuming the emissivity of the surface to be constant, the ratio of the temperature T1 by T2 is. It's very easy. We know that Stephen Boltzmann says, yes, that is right. That is correct. That emissive power of a black body is directly proportional to T2 to the power 4. Okay. So of a real body, it will be like this. But emissivity remains constant. Yes. 2 mark question. I think it is 2 marks. I think it is 2 marks only. Okay. I mean, do not focus on marks. Just see that it has come. I mean, this type of question has come. Okay, very nice. So, okay, so emissivity is proportional to T to the power 4. Now I can say E1 by E2 is equals to T1 by T2 to the power 4. So T1 by T2 is equals to T1 by E2 1 by 4 or 0.25. And you have calculated it already. It's 500 by 1200, 0.25. And you have given me the answer 0.8034 is the right answer. Very nice. Yes. 2 mark question. Usually, look, I do not do mistakes as much, like it must be of 2 mark only, but I'm not saying that, like I'm perfect, I cannot do mistakes. Because sometimes when I, when I make slides, so I do some copy paste. For example, titles I can copy, these things I can copy. Sometimes I forget to edit because my focus is on the question, not on the extra information. But still, I try to be right most of the time, but I can go wrong. Okay, it's not that I can be perfect. ठीक है, चलो next question. Two large parallel plates having a gap of 10 millimeter in between that are maintained at temperature T1 and T2. भाई ठीक है, 2 plates हैं हमारे पास. One is maintained at T1 1000 Kelvin and T2 400 Kelvin. Emissivity is also given Emissivity 1 is equals to 0.5. Emissivity 2 is equals to 0.25. Emissivity 2 is equals to 0.25. Stephen, the Boltzmann's law constant is given. Heat transfer between plates. It is what we are doing from then. It's very simple. That's why I was saying radiation is a topic that is very important and very easy to score. Very similar kind of questions from view factor. You see, we solved view factor questions that day. Most of the questions are similar. Like there is very few modifications that can be done. The same formula is there. The same repetition you need to do. Some 2-3 rules that you have to apply, and that's all. And this also, not much modification is done. My area is equals to sigma. Yes, that is correct. Sign is correct. Okay. चलो T1 to the power 4 minus T to the power 4 upon 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1. Very easy. Very easy, right? Sean is also correct. Sean is everything we know already. There is nothing that we don't know. And 2-mark question. Shouldn't take more than 15 to 20 seconds to solve this. Shouldn't take more than 15-20 seconds to solve this in exam. Shruti, did you get the answer? Shruti is there or not? Okay. Okay. Yes, 11.05 kilowatt. 11.0 watt kilowatt per meter square. Okay, very nice. Chalo, let's move on to the last question. Two infinite parallel plates are placed at a certain distance apart. An infinite length radiation shield. So now we have inserted a radiation shield in this. This is one shield. Okay. And these things are insulated from the outside. Now, an infinite length radiation shield is inserted between the plates without touching any of them to reduce heat exchange between the plates. Assume that the emissivity of the plates, ये कह रहा है, it is saying emissivity of, if this is 1, this is 2 and this is 3. So 2, 3, they are same and it is equals to emissivity. The ratio of net exchange between the plates without and with and without the shields. So it is asking Q dot with shield upon Q dot without shield, and I have already defined it for you. It is 1 upon n plus 1. Very simple. Otherwise, if you don't remember this, you can go back to the basics and define that. Okay, because we all know that this is valid. You can define all the resistances. It will take you more than 1 minute or 1.5 minutes to do that. But we already summarized it, right? And we know by F11 is equals to 0, F22 is equals to 0, F33 is equals to 0. And we can define other things as well, and we can conclude our this thing. Okay. Chalo. One shield is there, 1 plus 1. And 1 by 2 is my correct answer. Okay, A is the correct answer. Chalo. Now this is was the last question. Now I think Vijaya have sent me one question. If you want to stay, you can stay to solve that question as well with us. Otherwise, we are done with today's class. Now I need one slide also. Where do I solve this? Chalo, okay, we can try to solve it here. What was your opinion on GATE 2000 paper HT? I have to look upon the questions. I looked I saw them long time back, है ना? Actually, I have solved few questions as well. But I have to again now. If I have to comment, I have to look it again. I don't remember the question exactly. Okay, I have to see it one more time. I have actually solved ESC paper and GATE 2022 paper, but ESC paper was actually long. It was quite long and not very tough, but very long. GATE I need to check again because it was in Feb. Okay, so long time back. Chalo, ठीक है. So let's go to Vijaya. Do you want to solve that question? Okay, chalo, ठीक है. Let me try. Let me see what you have sent me. Chalo. Okay. I need some space here for it. चलो ठीक है. Okay. A copper sphere is suspended in an evacuated room maintained at 300 Kelvin. We have a room and it is suspended. A sphere is suspended. Sphere is suspended. And room is maintained at 300 Kelvin. Room is maintained at 300 Kelvin, while this sphere is maintained at 500 Kelvin. By providing electricity of 210 watt. Okay, so how are we maintaining this at 500 Kelvin? By supplying electricity. So we are supplying electricity how much? 200. So it is like this. It is 1 second. It's like a bulb only. Okay, so it is something like this. It is a wire and it is some resistances and it is the sphere. Okay, so it is maintained at 500 Kelvin by supplying electrical power of 210 watts. When the surface of the copper sphere is completely blackened, 700 watts is needed to maintain same temperature. Now, when you have completely blackened, now if you have completely blackened, now how much do you need? Now electrical work is 700 watts is needed to maintain the same temperature of 500 Kelvin. The emissivity of copper. Now you tell me one thing. How would you calculate the emissivity? By emissivity, how would you calculate the emissivity of this? Emissivity will only come when it is not blackened. Otherwise, if it is blackened, emissivity will be equal to 1. Emissivity is very high. That's why you need to give power. That's why you need to give more power. I can't. Let me go back to your chat so that I can see the comments. Okay. Okay. Yes. 700 watts. Yeah. I mean, the thing is that 700 watts you are giving when its emissivity is equals to 1, isn't it? When it is blackened. Do you understand this point or not? Its emissivity is increased. That's why you are giving more power to maintain the same temperature. But its emissivity will have a finite value when it is not blackened. So I need to find out that emissivity. I can find out that emissivity. Are you able to understand that point or not? Let me read the question one more time for you. Let me see. Let me go back. And it is saying, look, a copper sphere is suspended in an evacuated room maintained at 300 Kelvin. Now the sphere is maintained at the temperature of 500 Kelvin by providing electricity of 210 watts. When the surface of copper sphere is completely blackened, then we need 700 watt to maintain the same temperature. Now they are asking emissivity. So of course emissivity, do you have options? Option 1, emissivity is equals to 1 cannot, I don't think it will be there because it's very obvious. Okay, do you have option in option or not? Emissivity 1. Yes, it's very simple, no? You have calculated. Sean has told me this. Okay, numerical answer type. Okay, it's okay. So anyway, you can, as he has also told me that this body, Sean has also told that if this body E is equals to emissivity EB, right? So EB that you are giving is 700. Emissivity will equals to E upon EB, and this is 700 by, I'm sorry, 210 by 700 is equals to 0.3. Sean has what he said. It is also correct. Also, you can find out emissivity by another way. What is the another way? By, you know that it is not blackened. Then only emissivity could be find out. Okay. So whatever heat that you are giving, will be equals to its emissivity sigma A of sphere T of sphere to the power 4 minus T naught to the power 4. Now, how much heat you are adding? How much heat you are adding? Can you tell me how much heat you are adding? What is Q12? Can you tell me? Why 490? Array 21, this electrical, whatever electrical work that you are giving will be converted to heat, no? Why 490? Whatever electrical power that you are giving will be converted into heat. That is the resistance, right? So 2110 is equals to emissivity. You need to calculate sigma, you know, 5.67 into 10 power minus 8. Area of sphere, you know, and sphere temperature is 500 to the power 4 minus 300 to the power 4. I think you will get the same answer. Can you calculate this? I think that you will get the same answer. Can you calculate it for me and tell me how much is emissivity? Okay, no, as not given. What is not given? अच्छा, area is not given. Area is not given. So then, तो फिर you can. अच्छा, 1 second. Let me check one more time. If area is not given, then you can direct. Then you can use this only. And this is the only way. Yes, nothing is given about area. So that is the only way that you can calculate. Okay. Or you can also do it like by, it is 700 is equals to 1 into sigma into a sphere. Now this is same temperature you want to maintain, minus 300 to the power 4, and you divide this equation. You can find out emissivity. Everything will be cancelled. Right? This is also another way of doing it. ठीक है? चलो, very nice. Now tell me one thing that we are going to start. Yes, who is this?
Me only, sir. Vijay.
Tell me.
Sir, what happened means in gate 22 when I appeared for examination, when I read the e-transfer question, when I go from the start to end, I forget the first part, sir. That is why I'm asking, is it
You
easy or
forget the first part. What part? Conduction part.
no? Means while
Huh.
reading the question, because the questions are very lengthy, sir, in gate
Okay, okay,
2022.
okay, 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 okay.
While
So yeah,
reading,
we need. Tell me, tell me.
uh, we are not getting what he was telling because the length of the question was too high and I have wasted around 18 minutes for one question in last 30 minutes, sir.
No, 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 no. Look, the thing is that, for example, there are few questions. For example, in thermodynamics, unsteady questions are very lengthy. Okay, but you know that what data you need to extract. That is very important from those questions. So if these type of questions are there, then you have to attempt those questions. If you see, look, once you have read one question, you can skip that question. Skip, like, skimming is a method of reading something. So you can skim the question. Skim means you can read important parts of it. You can just overlook the question in 30 seconds or 45 seconds if it is a long question. If it is a short question, you sometimes you are able to do that question in even 45 seconds. But if it is a very big question, in 30-45 seconds you can skim that question, and by skimming you would understand that will you be able to do it in short amount of time or not. If you think that it will going to take some time, then leave that question. Even if you know that question, leave that question. Do it in the end. Once you have done all the questions that you are confident in, then only it is possible. I mean, that only it makes sense, because by doing that question, even if you know that question, if you have wasted 2-3 minutes in that, no, then that means you will rush on to the questions that are easy and that are short. You will get some good marks, right marks for those questions. So you will rush on those questions, and then there's a possibility that you do them wrong, and just for getting 2 marks, now you have wasted 3 or 4 marks. Okay, so do 1 mark question quickly, 2 marks question, whatever you see. First of all, do all the questions that you are most comfortable in, that takes very less time. And once you have done that, then you have no hurry of doing questions, because even if you are attempting some questions that you don't know, it's not very harmful that you are giving much more time, because you're not losing anything, you're only getting something. Okay, so try to do something that, like, first of all, attempt what you have already done. I'm sorry, first of all, try to attempt that you can, that you are most comfortable in, that you think that it will take less time, and it's very short that I'll get these marks. Okay, chalo. Otherwise, once I'll see the question, then I can comment on that, because now I don't remember. It was a long time back. Okay, chalo. Now again, tell me one thing. Look, tomorrow's class will be long for sure. I cannot do anything about it. I need to cover few concepts, and I must cover it in one class. Okay. So everyone, tomorrow class will, I will look again. I will tell you my approach for convection. Look, there are so many derivations. There is continuity or mass conservation equation. Just, are you all there, or you have left it already? Just let me check. Okay, you are all there. Okay. Okay. So one thing is, and a mass conservation is there. Okay, and then momentum conservation is there. Then energy conservation is there. Then boundary layers are there, which is thermal and hydrodynamic boundary. Thermal and hydrodynamic. Then solutions are there of these equations. Okay. And then both are for external and internal flows. Then we have free convection. Then we have other concept as well. But the point here is that, the we can do all the derivations. Even you can download by, I don't know if I'm allowed to tell you this, but I have, it is all in recorded form. If you want, I can tell you the, where you can get the recorded form, and you can do your convection in 7 to 8 hours. More than that, maybe, maybe 10-12 hours, because I have done all the derivations there in detail. I have simplified. I have put all the equations, put all the boundary conditions, solved them. But it is not. It is at this point it is not useful for us because we are at very last level of our preparation. If I do convection in last 10-12 hours, it doesn't make any sense. Okay, so what will I do? Yes, questions are also, the number of questions that are asked is very less. The possibility of asking question is very less. So there is no point that we spend 10-12 hours on convection and then you won't even revise it. I know that you are not going to revise it. Okay, so what we will do, I will give you the conclusions, I will give you the equations, I will give you the solutions, I will give you the flow of how it is happening, but we will not go into detail. Okay, and even if we are not going to we will not go into detail, it is going to take around 6 hours, 5 to 6 hours. Okay, chalo. So what I am going to do tomorrow, we will talk about external flows, and then I need to cover everything in this. So it is going to take, let's say, more than 2 hours for sure. We will try because there is not much explanation in that, but we will try to finish it in time. Even though, if needed be, I'll try to extend the class for whatever time it is, like maybe 2.5 hours or 2 hour 15 minutes or whatever it is. Then next day, I have to cover few concepts and then questions. So that if you want, I can distribute it into two classes or one class. I can cover it into one class. So it's okay. You can decide it. You can think about it. You can tell me tomorrow, no problem. Okay. But this class and if tomorrow class will be little long. So if we start at 5:50, so 6:50, 7:50. So let's say around 8:15, 8:20, we will finish the class. Or 8:30, right? Chalo. So tomorrow we will meet for convection. And if you want, we can finish convection on Sunday. Everything we can finish. Otherwise, if you want to leave questions for next time, you can leave. I don't have any problem. You can decide. ठीक है चलो. I would prefer that we finish convection on Sunday. चलो ठीक है. Can we go for free also tomorrow? No, we cannot. It will be then very long. It will go more than 6 hours. Okay, it will go very long. No point in that. Yes, I know. Free convection we cover on Sunday. It is also no. Look, tomorrow we will only cover external. Internal will be covered on Sunday, and free convection will be covered on Sunday. Boiling will be covered on Sunday. Questions will be covered on Sunday if you agree. So it is too much. We cannot do it on the same day. You will stop. I mean, your mind will get saturated. There is no point. Okay. So let's cover only that amount that you can comprehend. Okay. ठीक है विजय. चलो. Let's meet tomorrow at 5:50 and we will continue our class till 8:15 or something. Let's say, I hope that we will be able to cover that. ठीक है? चलो. So I will see you tomorrow. Tata, bye bye. चलो.